Alright everyone, so we're ready to move on to chapter 10. This is our first material after break. What we're going to do is I'm going to do a few videos here over chapter 10. The first one is I just want to give you the kind of overview of what we're going to do. And then we'll actually go through and work some examples. And then after that I actually want to do a third video where I'm going to show you how to do all these commands with R. Because this is the chapter where R really starts to be super useful for all of these tests, and a lot of stuff is actually built in for R. So if you remember, I said in class that R is not really going to work that well for doing things like the Z test, but it does do really well with the T test. So I'll do a third video soon showing you all the details about the T test and all the different capabilities that R has for that. So before we do that, though, let's talk about chapter 10. The ideas that we're going to study, I guess actually I should mention just real quick that in chapter 9, remember that we were talking about inferences for one population mean. So we had some sample of data and we wanted to know what is the population mean probably, right? So we could find confidence intervals, which we did in chapter 8. We could do things like hypothesis testing, say we're going to guess that our mean is this value, within 5% significance. Is that true? Does our data bear that out? And so that's one population mean inference testing. So here we're going to do inferences for two population means, and the ideas are going to be the same. We're going to have two populations, and we're going to just kind of assume different things about these populations. I'll go through that in a second. But we're going to have two populations. Let's say we have, maybe they could both be normally distributed, so maybe they're both going to be, maybe one will look like that and the other will look like that. Who knows? But what we're going to do is we're going to try and figure out, are the two underlying populations going to have the same mean or not, right? So our null hypothesis is always going to be that nothing happens, right? That's what the null hypothesis is. And so our null hypothesis is that they're going to be the same. The two population means mu1 and mu2 are going to be equal. And then we can have one of three alternative hypotheses, just like we did before, just like in the previous chapter. We can say that maybe the means are not equal, so that would be a two-tailed hypothesis. Maybe our alternative hypothesis is that the first mean is less than the second, or the first one's more than the second, right? Those are the other two options. So it's left-tailed and right-tailed, respectively. Okay, there is a little bit of math involved in this chapter. Don't let it bother you. You'll have all the formulas on the formula sheet. You'll have this worksheet to also be able to reference during the exam. And then I'll give you, just like in the last section, or the last chapter rather, I'll give you a worksheet of all the R commands, all the R codes that I went over. And then I'll also have the videos. So R is really going to be helpful in this section. So what we're going to do is we're going to assume that x is a normally distributed variable on one of two populations, n1 and n2. Remember, n stands for the sample size. So this is the sample size of the first sample and the sample size of the second sample, okay, from the two populations. Mu1 and mu2 are the means of the populations, the population 1 and population 2. Sigma 1, sigma 2 are the standard deviations of the populations 1 and 2. And just like usual, S1 and S2 stand for the sample standard deviations, and likewise X bar stands for the sample mean. Okay, so it's all the same. It's all the same stuff. So mu, I think this is just worth writing down. Mu refers to the population mean, so this is the same stuff as before. Sigma refers to the population standard deviation. X bar stands for the sample mean. Okay, so the sample mean. S is the sample standard deviation. And then N stands for the sample size. Okay, so if we put a subscript on here, if we put a subscript of 1 on here, that means that these are just all the terms for the first population. If we put a subscript 2, that means that we're talking about the second population. Other than that, everything is fine. It turns out that under our hypotheses that x is a normally distributed variable, then the mean of the differences, so if you look at, this is a little bit of a setup here, but the idea is that what you're going to look at is, remember what we're doing is we have two populations. We want to know, are their means equal or not, right? We want to know, is mu1 equal to mu2? And so what we're going to do is we're going to look at the two different samples, and the two different samples will have whatever sample means are associated with them, right? So x1 and x2 are going to be the sample means. And then if you look at the difference of those sample means, that's going to be the mean. Okay, that's going to be our mean variable here. Okay, so that's going to play the role of our mean. If you look at the standard deviation for the differences, that's going to be given by the following formula. So again, a little bit of math here, but it's just everything that we need to know is in these formulas and everything's fine. And so our standard deviation is going to be this value, so the square root of sigma 1 squared over n1 plus sigma 2 squared over n2, right? We take the square root of the whole thing. Again, n1 and n2 are the sample sizes of the first and second population, okay? And then with that being said, we can find the standardized version. Standardized version is where you just use the standard deviations, right? The population standard deviations. Right, so standardized means that we know the population standard deviation. Everything's fine. Okay, we don't really have too much else to say here. So that's the standardized version. In practice, that's never going to come up. We're not even going to bother to go through any examples with that. It's just that this is what happens under all of our new assumptions, right? So if we have a mean that's mu1 minus mu2, and if we have a standard deviation that's that formula, then when you look at, remember that the standardized variable of anything is z is going to be x bar minus mu divided by sigma over square root of n. This is kind of the relevant analog of that formula for this problem. So these are our formulas. But again, it's never going to be that we'll use the standardized version. That's just not tenable in practice, right? If you know, it's just very unlikely. If you know the population standard deviations, then you also probably know the, if you know the population standard deviations, you also probably know the population means, right? Anyways, so here's the thing that we're going to do with this. We're going to assume we're going to have two cases here. Really, what we're going to do, and these from here on out, these are all going to be t-tests. We're not going to assume that we know the population standard deviation of any of the populations that we're studying. But there's still two cases to consider. Even if we don't know what the actual value of the population standard deviations are, if we have a reason to believe that those population standard deviations are equal, okay, so if we think that sigma 1 is equal to sigma 2, then many things get simplified, namely the standard deviation. You can, if this is equal to sigma squared, right, and then this is sigma squared, then you can factor that out. After you take a square root of sigma squared, you get sigma, because sigma is positive, and then you can use that as your standard deviation formula, right? The problem with that is that if you don't know the standard deviation, what you have to do is you have to use the sample standard deviations. And what we did before is we just could put in S for our sample standard deviation before, right? But now what we need to do is be a little bit more careful because we have two sample standard deviations to use. So we have to use what's called a pooled standard deviation. This is a way of combining the two standard deviations into a single number. Okay, it's almost like, in fact it is, taking a certain weighted average of the two numbers. Okay, and so it turns out that this is the right formula to look at. That's called the pooled standard deviation. It's again just a way to take the average of the two standard deviations. And then if you look at the pooled standard deviation, that's exactly the value that we should put in for sigma. And then we have a test statistic with the t-distribution. And so our test statistic is t is x1 minus x1 bar minus x2 bar minus mu1 minus mu2 all over the standard deviation divided by the square root of n, except in our case it's really it's times the square root of 1 over n1 plus 1 over n2. Okay. I should actually point out, maybe I should rewrite this just to be a little bit clearer. Actually, before I say this, if in our hypothesis testing mu1 is equal to mu2, if that's our null hypothesis, that actually really simplifies our test statistic t, right? So if mu1 is equal to mu2, then that mu1 minus mu2 is 0. And so what we end up with is our test statistic here. And just to be clear, I just want to rewrite this. This is going to be x1 bar minus x2 bar all over s sub p times the square root of, I just want to be careful about where all the numbers go, 1 over n1, 1 over n1 plus 1 over n2. Okay, so that's our test statistic. So when we write 1 over n1 plus 1 over n2, that's the order of operations, right, that we mean. All right, so that's called the pooled t-test because you're pooling the standard deviations. You can also do things like talk about confidence intervals. This, again, is perfectly straightforward. We have a nice formula for it. There's the formula. We'll use that formula occasionally. Okay, this, again, mimics the confidence interval formula that we had before. So if you remember in the last chapter, we had that our confidence interval was x bar plus or minus t sub alpha over 2 times our standard deviation over square root of n. Okay, here we have, that's a plus or minus there. So here we have two populations, so we have to, instead of saying square root of n, we have to replace it with the relevant term there. We have to use a pooled standard deviation. Rather than x bar, we're talking about the difference in the means, x1 bar minus x2 bar. Other than that, it's actually the same formula. Okay, so it's yeah, the same formula. That's a 1 minus alpha times 100% confidence interval. Okay. If we are not assuming that the underlying populations have the same standard deviation, then we use what's called the non-pooled t-test, or it's actually someone that pioneered this. It's named after them. It's called the Welch's t-test. Okay, that's what R actually refers to it as, Welch's t-test. And here, we're not necessarily assuming that the standard populations, the population standard deviations are different. We're just not assuming that they're equal. So maybe they're equal, maybe they're not. We're not assuming anything ahead of time. And under that assumption, this is called the non-pooled t-test. Okay? And again, a little bit of math here. The test statistic is the same, right? If you go back and if you trace everything through, this is the test statistic that we're going to use. Okay, so I think it's worth just scrolling up for just 1 second to look at the similarities here. This is the test statistic that we're going to use, right? It's that value. You replace the sigmas with s's, okay, because we don't know the population standard deviation. And again, mu1 minus mu2 is 0. The only difference here is that this is going to satisfy the t-distribution, okay, but the degrees of freedom you have to calculate. So here, so before, I should have emphasized this, our degrees of freedom is going to be the sum of the degrees of freedom of the two samples. So if you take n1, so n1 minus 1 plus n2 minus 1, right, that's the degrees of freedom of each of the samples. And if you add those up, you end up with n1 plus n2 minus 2. Okay, so the degrees of freedom is straightforward for the pooled t-test, but the pooled standard deviation is kind of a mess. Okay, so that part's harder. For the non-pooled t-test, it's the opposite. So for the non-pooled t-test, the degrees of freedom is kind of a pain to compute, but the standard deviations are easy enough. Okay, so it turns out that the right degrees of freedom for this is given by this mess of a formula. Okay, and in general, this is not going to be an integer. So what you do is that if this number turns out to be, say, whatever, 43.7, your degrees of freedom will be 43, right? You always round down to the nearest integer. Okay, so you round down. All right. You can again do confidence intervals. The formula is identical. Okay, so not much to say there. So that's how you get confidence intervals for the non-pooled t-test. And that's really all I wanted to say about those two. There's one more thing that's going to appear in our chapter, and we're going to skip over 10.4, but we're going to talk about 10.5. And here what we're going to do is we're going to talk about kind of studying two different population means using paired samples. Okay, and so the way that this works is that you're going to have two samples, say x1 to xn and y1 to yn. They have to be the same length, otherwise this test isn't going to work. And what you're going to do is you're going to look at the paired differences of the two samples. So what that means is you're going to look at x1 minus y1, x2 minus y2, all the way down to xn minus yn, and you're going to record what those differences are, d1, d2 to dn. So these d sub I are the differences. And then what you do is you study this variable. You kind of treat d1, d2 all the way to dn as your new sample. Okay, so that's the idea. Okay, and so once you have just a single value that you can study, then you can revert to the ways of chapter 9. Okay, and you can do things like, you can do the t-test. The t-test has the usual nice formula. Okay, so it's going to be the mean divided by the standard deviation over the square root of n. Okay, and that's going to have the t-distribution with n minus 1 degrees of freedom. And you can talk about confidence intervals. So here instead of x bar and instead of s, we have d bar and s sub d. Other than that, it's exactly the same. That's the entire overview of chapter 10. Okay, so again, we're going to study two populations and try and figure out do those populations have the same mean or not. Okay. All right, next we will do some